Okay, so in today's lecture, I am going to start introducing organometallic reactions like the Heck, Suzuki, Stille. We will start with the Heck reaction. For quiz number 3, uh, despite going over individual reactions like transmetallation, migratory insertion, oxidative addition, I didn't want to test you on the individual reactions because the individual reactions alone don't really make sense. You kind of have to put them together in the correct order um, to sort of understand their relevance. And so what we'll do in this lecture is start putting a few of them together, and we'll start off with the Heck reaction. So the Heck reaction, as I previously mentioned when I first started introducing organometallics, was developed by Richard Heck. And he was one of the recipients of the 2010 Nobel Prize in Chemistry. The reason this is so important is that if you follow um, when the announcements for the Nobel Prize in Chemistry are made, which was, I think, Wednesday of last week, it's usually someone in biochemistry or protein chemistry. It's rarely given to an organic chemist or an organometallic chemist. And so this was a really big deal in 2010. And again, he was just one of 3 recipients. And so we'll talk about the other 2. But Richard Heck really set the foundation for cross-coupling reactions. And cross-coupling reactions just really means the formation of carbon-carbon bonds. Okay. So let me go ahead and introduce the general reaction. And then we'll go over the mechanism. And so the general reaction usually includes an aryl, vinyl, or alkyl system. If it is an alkyl system, it must not have beta hydrogens. And we'll talk about this as we're going along. X is our leaving group. And just like with SN2 and SN1, the best leaving groups are halogens, right? So chlorine, bromine, iodine. You can also use triflates, and we've seen triflates before when we were talking about boron triflates, oxazolidinones, and just to remind you what a triflate looks like. So these are all great leaving groups. You need an aryl halide or a vinyl halide or an alkyl halide, but your alkyl can have beta hydrogens. And again, I'll talk about why as we go through the mechanism. You need an alkene. And not just any alkene. Your alkene must have at least 1 hydrogen present. On the alkene carbon or on an alkene carbon. And so in this case, you can see there's at least 1 hydrogen present. The reaction is typically run with a palladium catalyst and a base like triethylamine, potassium carbonate, cesium carbonate, sodium bicarb. So it can be a nitrogen base or a salt base. Let me highlight these because you have to have both. And the product is the replacement of the hydrogen on the alkene with the R group. And so you have formed a new bond. Now, the relevance and the importance of this is that you're typically forming, especially if you're using an aryl or vinyl system, you're typically forming a carbon sp2 carbon sp2 bond, which is impossible to make with just organocatalysis, okay? Whether it's oxazolidinones, pseudoephedrins, Dave McMillan's work, you need a transition metal for this, okay? Our palladium catalyst is typically, but not limited to the following. It's a palladium with 2 triphenyl phosphines, which is 14 electrons. And because it's 14 electrons and we're under the 18 electron rule, then not surprisingly, it's got open coordination sites, so it can do chemistry and it can catalyze the reaction. Because it's also a catalyst, you must regenerate it at the end. Okay. Now, again, this isn't the only catalyst. I'm just teaching you the very basics. You can use other ligands. You can use chiral ligands. You're not limited to this specific catalyst. It's just the most popular catalyst that is used. So let's jump into a reaction and an example. And I'll give you not only the reaction, but the mechanism. We'll start off with an aryl bromide, an alpha beta unsaturated system. So this is R of alkene, of course, palladium triphenylphosphine, and I'll use triethylamine as our base. Okay. Now, typically when you do have more options on your alkene, the most favored product is the less sterically hindered product. And so the reaction is really driven by hindrance. And so we'll see that in the mechanism as well. And if you remember from your first semester organic chemistry, you typically want to form the trans product in order to avoid any sterics whatsoever. Okay. Okay, so let's jump into the mechanism and the catalytic cycle. And so mechanisms for organometallic reactions are typically drawn in circular form, and you'll see what I mean in a second. You start off with your palladium catalyst, which I just mentioned is 14 electrons. So I'll just go ahead and start adding that in, just so we can keep track of our electron count. The first step to the reaction is an oxidative addition reaction. And so make sure you go over lecture number 7 to see that was the first reaction that I taught you, oxidative addition. So I introduce my aryl bromide. And if you remember, oxidative addition is very similar to forming a Grignard reagent. The palladium inserts itself in between the carbon and the halogen. I'm just going to draw out phenyl because I don't want to keep drawing out the benzene ring or the phenyl ring, excuse me. So this is my oxidative addition product. This is 16 electrons. Total electron count. It's still unsaturated, right? So I still have an open coordination site. I go ahead and I add my alkene. My alkene coordinates to my palladium. And let me draw this carefully because there's a few things that you need to remember from lecture number 7. The first thing that you should note is that this already is at 18 electrons. So nothing else can be added to this. Okay, it is a saturated system. So everything that is occurring now, from now on, has to be within this complex. Okay, that's the first thing to note. The second thing to note is the fact that the next step is a migratory insertion. Because it's a migratory insertion, if you go back to lecture number 7, we talked about how alkenes inserted themselves into a palladium or metal complex. Okay. We talked about electron withdrawing groups being present as opposed to electron donating groups. This is an electron withdrawing group. Because that's an electron withdrawing group, my substituent adds to the least substituted carbon. And we talked about why. So please go back to those lectures. And we talked about migratory insertion and the arrows that you draw to show the migratory insertion. Okay. Now I can go ahead. And if you remember, migratory insertion is cis. So the phenyl and the palladium that are inserted into the double bond are inserted from the same side. And in this case, I just chose the top side. You can choose the bottom side. It doesn't matter whatsoever. Okay. Now I'm back to 16 electrons. Please notice that the next step, now that I've inserted my phenyl group, is to regenerate the double bond because my product has a double bond in it. And the way to do that is through a beta hydride elimination. The carbon next to the palladium or the metal is known as alpha. Next door to alpha is beta, and I've got my 2 beta hydrogens. Okay. Now, unfortunately, I can't just pick any beta hydrogen to be alpha. I need to pick the correct beta hydrogen. Oh, excuse me. I need to pick the correct beta hydrogen that's cis to my palladium in order to form the trans product. So what do I mean by that? Why can't I just pick any one of these 2 beta hydrogens? I can't. I have to be really specific about which one I pick to have it cis to my palladium. And I has to be this hydrogen. Y. So let's rotate that. I'm just going to redraw it. Rotate about carbon-carbon bond. Okay. And so I've got my purple beta hydrogen. Let me highlight that. Cis to my palladium, because I need to do a beta hydride elimination. And in order for a beta hydride elimination to occur, one of the hydrogens has to be cis, which means that if I rotate to put the purple hydrogen facing up, my phenyl group is now facing the back, and the other hydrogen is now wedged. Now I can do my beta hydride elimination. Now, the reason I chose the purple one is because I need the trans product. And if you notice, the phenyl group is dash, the ester group is wedged. They are set up perfectly to form the trans product once the beta hydride elimination occurs. And I form my alkene. And not just any alkene, right? My trans alkene. Let me move it up a little bit. Okay. If I had rotated it to put this hydrogen, let's do that. Rotate about carbon-carbon bond so that that hydrogen is cis to my palladium to set it up for the beta hydride elimination. Then my phenyl group would have been wedged, and my purple hydrogen beta would have been dashed. And if I set this up to form, that's a terrible arrow, the beta hydride elimination, I get the alkene, but I get the cis product, right? And I don't want that. I want to have my trans product. So beta hydride elimination. Let me write that down as well. Now, Dr. Lucero, this isn't the catalyst. How do we regenerate the catalyst? We're not done. We form the product, but that doesn't mean that we're done whatsoever. We go and generate the catalyst through a reductive elimination. So go back to lecture number 7. Okay. Reductive elimination is just the opposite of oxidative addition. And in order for reductive elimination to occur, I need my two substituents cis to each other, and I form hydrogen bromide, and I regenerate my catalyst. So RE, reductive elimination. So you can tell why it's cyclic. You have to regenerate your catalyst in the end. Okay, we're not quite done. We're almost there. The last couple of steps are super basic in the sense that they have nothing to do with the formation of our product anymore. Our reductive elimination just has to do with the formation of our regeneration of our catalyst. And then the final step is, Dr. Lucero, why are we adding base? We didn't use any of the base in this reaction. You're forming hydrogen bromide as your byproduct, which is an acid. So the very last step is to neutralize your reaction. And to form a salt. And so the base is typically thought of as catalyzing the reductive elimination step because it wants something to deprotonate. And in order to deprotonate something, you need to form an acid. And so the reductive elimination step is catalyzed by the formation of triethylamine. The triethylamine is just waiting to deprotonate something. And so the minute the reductive elimination occurs, it starts deprotonating your acid. And so the base is incredibly important for this reaction. Okay. Let me show you a few more examples. And we'll do a few mechanisms as well, just to get you used to the catalytic cycle. Some of them might be obvious, some of them might not be obvious, and that's perfectly fine. So in this case, please notice that we have a vinyl bromide, our alkene. Not surprisingly, just like in our previous example, we are going to form the trans product, regardless of how many hydrogens are on our alkene. It's an incredibly specific reaction where you're trying to avoid sterics. And so you are forming your new carbon sp2 bond. Now let's try it with an electron donating group on our alkene. Again, go back to lecture number 7, part 2 and 3. We talked about the fact, what if you have electron withdrawing groups versus electron donating groups, electron withdrawing groups? You're always going to add the new substituent, to the least substituted carbon, whereas when you've got an electron donating group, you added to the more substituted carbon. And we talked about why, okay? Regardless of where you're adding it, you're forming a new carbon sp2 bond. Okay. Let me go ahead and introduce the following. This is a reaction that we do in our lab. We use potassium carbonate and it couples to the top. Notice that it's the trans product that is formed. Oh, sorry. Let me write carbon sp2, carbon sp2 bond, and it is still trans. Okay. One of the last reactions that I do want to go over and the mechanism is the following. Please notice that I am using a vinyl bromide and again, an alpha beta unsaturated ester. And so this kind of looks tricky, right? And tricky because it's an alpha beta unsaturated ester where the trans position is already being occupied. Okay. But the product of this reaction is as follows. Notice how the new bond is still trans. New carbon sp2, carbon sp2 bond. Notice that despite the new bond being formed, it is still holding up its uh, cis 3D structure. Okay. Really clever how they did this. So let's talk about the mechanism. And just like before, you start off with your palladium catalyst. So despite the fact that there's hydrogens present on our alkene, and there's two different hydrogens present on our alkene, it chose a very specific site of where it's introduced. And it kept its cis isomer. So let's start with the mechanism. Just like before, it's a circular catalytic cycle, so I need to get back to where I started. Our first step is our oxidative addition. And I don't know if you remember, but in lecture number 7, I said typically our first step and our last step are oxidative addition and reductive elimination. It's rare when that's not the case, and we'll talk about those cases. But in this case, our first step is always oxidative addition. Our last step is always reductive elimination to get us back to our catalyst. We've got our vinyl bromide. And just like before, it looks very similar to the formation of a Grignard reagent. So the palladium inserts itself between the carbon and the bromine. Okay. Just like before, we've got 14 electrons, 16 electrons. You're more than welcome to continue counting just to make sure you've got the right electron count. Just like before, you introduce your alkene. In this case, your alpha beta unsaturated system. Let me draw my arrow a little longer. Okay. Now remember, You're always inserting when it comes to alpha beta unsaturated systems, i.e., you've got an electron withdrawing group, you always insert your alkyl group to the beta carbon, right? That's the most electrophilic carbon. Please go back to lecture number 7. That's the most electrophilic carbon. Let me try to draw this as best as I possibly can to show you, one, it's too crowded. The alkene complexing to my palladium, but the only reason that I just moved the triphenylphosphine was to have some space for my ester. Okay. Now that it's complexing to my palladium, it's at a late 18 electron count. Now I can go ahead and do my migratory insertion. Let me draw this in red arrows. Notice that it's the electrons bonded from the palladium and the carbon sp2 that are adding to your beta carbon, and it's your double bond that's attacking the palladium. Again, it adds in a cis or syn fashion. Which means that they're facing up. And if you've noticed, I like to draw them up. You don't have to draw them up. If you don't want to, you can draw it from the bottom side as well. Oh, excuse me. Okay. Before I move forward, just to keep track of everything, my palladium and the new introduced group are cis to each other. Okay. That's the first thing. You've got the syn addition for migratory insertion. Perfectly fine. This is what I'm worried about. The other thing is, if my alkene is trans, when my palladium and my substituent add, my ester and my methyl group must remain trans as well. So I drew my ester dash and my methyl wedge. You could have drawn your ester wedged and your methyl dashed. Doesn't matter. The product is going to be exactly the same. It doesn't matter whatsoever. You just have to make sure 2 things. You add your palladium and your substituent syn, and if there is a specific isomer that you're using, in this case, the trans isomer, then you maintain that trans stereochemistry as well. It translates into the product as well. Okay. Okay. Now I have to go ahead and do my beta hydride elimination, but I don't have a hydrogen that's syn to my palladium. And luckily for me, in this case, I only have 1 hydrogen. So I have to rotate to get that hydrogen syn or cis to my palladium. That's the one I'm worried about. So once I rotate, oh, that arrow is supposed to mean rotate. About carbon-carbon bond. I'm going to leave my alpha carbon alone because that's not the one that changes position. The the palladium is fine where it's at. Sorry. Just wanted to make sure it was CO2Me, my ester. Now I can go ahead, if I rotated, have my hydrogen send to my palladium, but that means that my methyl group is now dashed and my vinyl group is now wedged. Okay. Now I'm set up for my beta hydride elimination. Now I've got exactly what I want, my palladium and my hydrogen. Can do my beta hydride elimination. And as the name implies, it's a hydride. So it's the electrons that attack and form my double bond. So let me draw out my product. I have a double bond. I've got an ester on one side. Notice how my methyl and my ester are both dashed, which means that they are syn to each other in my product. And my vinyl group is trans. Do you guys see that? Really clever. And of course, I have formed my palladium, bromide, hydrogen. Not the catalyst. In this reaction, we use triethylamine as our base. Our triethylamine wants to go after a proton, and in order to go after a proton, we have to do a reductive elimination. To get our catalyst and to get our hydrogen bromide, and now our triethylamine can form a salt after it's deprotonated the acid. Okay. Really clever the way it does it. I just have a few more examples, just one last example, and I'll finish off this lecture portion with why you can only use aryl halides, vinyl halides, and alkyl halides. But these alkyl halides cannot have beta hydrogens. So let me do another example. And then we'll move on to that explanation. Let me give you the starting materials first, and then just briefly talk about a few things, including the mechanism. Okay. Oh, excuse me. So the first thing that I want to talk about is this specific dark dot. This bold dot means hydrogen, specifically wedged hydrogen. So organic chemists, instead of drawing wedges and dashes, or specifically wedges, what we do instead is we draw a bold dot to indicate that it is a wedged hydrogen, okay? Which means that if this is a wedged hydrogen, then this is automatically dashed. So instead of adding wedges and dashes, we just draw in the bold dot to indicate your hydrogen is wedged, so your substituent must be dashed. Okay? That's the first thing. The second thing is that this is an intramolecular heck reaction. Intra, don't forget, is the reactions all occurring within the same molecule. Intermolecular means two starting materials. Intra means one starting material because everything's occurring in the same molecule. So this is an intramolecular heck reaction. We've got our vinyl halide and we've got our alkene. So typically when you have an intramolecular reaction, you're forming rings, right? Because everything's happening within the same molecule. Your product is typically the formation of a ring. And so the product in this case is the following. Now, here's what I want you to note. Again, I've drawn bold dots, which means that in both carbons, I've got wedged hydrogens, which means that my substituents must be dashed. Okay? So let's go ahead and jump straight into the mechanism. Before I do that, let me redraw these so that you can see what I mean. Again, the bold dot means a wedged hydrogen. And so in this case, I should have two wedged hydrogens and my dashed substituents. Now, because this looks a little complicated, that's why we use the bold dots. Okay? So let's jump into the mechanism. And just like before, we start with our palladium catalyst. Keep track of your electron count, but if you've noticed, it follows the same steps. Oxidative addition, alkene complexes to our palladium, migratory insertion. If we have to rotate, then we rotate, which we typically do have to do, right? And then beta hydride elimination, reductive elimination. Steps remain the same throughout the Heck reaction. So let's start with our palladium catalyst. We have our oxidative addition. Let me remind you, got a little crowded, sorry. So that's our starting material. Just like before, the palladium inserts itself between the carbon and the halogen. It's just that everything else is coming along with it. Okay. Please notice that now this is the part where the alkene complexes to the palladium. But luckily for us, the first thing is that the alkene is already part of our molecule. So it's right there and it can start complexing to the palladium. That's the first thing. The other thing that I want to talk about is the fact that, as I showed you, This substituent is dashed, so it's facing into the page. Because it's facing into the page, everything on this substituent is facing into the page. And what I mean by that is everything is facing into the page, right? This is setting the tone of your stereochemistry. Okay. And so my palladium is complexing to my alkene from the back. It's already set the tone for us of where the palladium and how the palladium is going to insert itself. And just like before, we have a migratory insertion. Again, because this is dashed, this is inserting from the back. So if you notice, our product is dashed because it's inserting from the back. This set the tone already. So now what we've got is you need to number this. Please notice that I've drawn the bold dot to indicate that carbon 4 is dashed. That means that palladium is also dashed. So my substituent and my palladium are still syn to each other. Nothing has changed. The rules haven't changed whatsoever. Okay. Still syn or cis addition. Okay. Now here's the problem. I need a syn hydrogen for beta hydride elimination, right? I still need to do my beta hydride elimination. But rings don't rotate, okay? Rings don't rotate at all. Please notice that my hydrogen is wedged. It is not syn. And so because it can't do a rotation, the next thing that it does, it looks for the next door hydrogen. And that's why you notice in the product, the double bond walked around the ring. So now it says, hey, this is a bold hydrogen, a wedged hydrogen. I can't rotate. So I am going to take the next best thing, the hydrogen next door. The mechanism hasn't changed. Again, I've got 2 beta carbons, which means I've got beta hydrogens on the other side as well. I do my beta hydride elimination. I form my product, which is exactly what I wanted. And let me do the phenylphosphine hydrogen iodide. I do my reductive elimination to regenerate my catalyst. And I form my acid, which now my triethylamine can come in and deprotonate to form the salt. Okay. The rules haven't changed whatsoever. It's just all intermolecular. But once you add things intramolecular, you need to make sure that you can find, hey, do I have other places I can go to get my beta hydride? Okay, because I'm not allowed to rotate. Okay, remember, you can't rotate rings, right? Can't rotate carbon-carbon bonds in rings. It's just impossible. You're going to break them. Okay, so now let's jump into why we can't use alkyl halides with beta hydrogens. We've given you examples of aryl halides. We've given you examples with vinyl halides. You can use alkyl halides. You can't use alkyl halides with beta hydrogens. So what do I mean by that? So something like this cannot be used. So why? So let's look at the mechanism. Let's say we use bromopropane. Okay. Let's start our mechanism. Just like we would and like we did the previous. Just like before, we do an oxidative addition. The palladium inserts itself between the carbon and the halogen. Okay. Now this is the part where we introduce our alkene, right? This is when we typically introduce our alkene, it does a migratory insertion. Okay. But instead of doing that, what it ends up doing is because we have beta hydrogens, because our propane has beta hydrogens, it ends up doing a beta hydride elimination. And the beta hydride elimination is a lot faster than introducing the alkene because the beta hydride elimination, everything's occurring within the same molecule. It's easier to do the beta hydride elimination because everything is in the same molecule, as opposed to going to look for the alkene so it can start complexing to the palladium. It takes longer to go look for the alkene so that the alkene complexes to the palladium, as opposed to everything occurring. So the minute you have a beta hydrogen, your reaction is dead. You can't do that. You're going to go ahead and go through the other route of a beta hydride elimination to form an alkene. Okay. So you typically don't want to have beta hydrogens. If you do have something big, then you typically want it to be highly substituted, right? You don't want any beta hydrogens. You want substituents on it. Okay. So you can use benzyl bromide. It's still a carbon sp3 bonded to bromine, but there's no beta hydrogens. Okay. So it shouldn't come as a surprise that trying to figure out how to add alkyl systems like bromopropane or alkyl systems with beta hydrogens and avoid beta hydride elimination has been a really hot topic in organometallics because it's really hard to stop the beta hydride elimination from occurring. And it's really hard because it's an intramolecular reactions, and intramolecular reactions are a lot faster than inter. It's easier for everything to happen within the same molecule as opposed to looking for the other molecule you're supposed to do your reaction with. Okay. Okay, you guys, I'll go ahead and stop here with respect to the Heck reaction.